Yeah. Okay, so we will. I'll share the screen, and all right. So I would like to know what are the things that you have finished up to what point, because today we'll just revise before I start. So what are you have finished completely Hartree Fock? Hello, am I audible?
Yes, sir. I
Yes,
mean,
yes.
Hatrafok is
Yeah.
almost done,
Yeah.
but I
So
think
you have some
my
questions, right?
case, actually, for my case, I need some recap of
Yeah,
basis
yeah.
set part will be better.
Okay, okay. So we'll see. And then anybody else has any other problems with Hartree Fock? Can I hear one by one? Hello. So somebody wants basis set, but the basic Hartree Fock theory can be done independent of the basis set. Is that clear? So the philosophy of the Hartree Fock had been that we still want to get a single determinant to solve the interacting Schrodinger equation. So that was the basic idea of the Hartree Fock, and because we know that a single determinant is not an exact solution, since it is an interacting problem, it's not a non-interacting Hamiltonian. So a we need to make approximations to do that, and that approximation is known as the Hartree Fock approximation. Is that clear to all? So some of the statements I want to know if you understand. So Hartree Fock is a process of trying to approximate by single determinant, and when you say approximate, it is the best possible approximation. There may be many single determinants, but the best possible approximation is what is known as the Hartree Fock method. So that is achieved by the so-called variation method. So you start. I don't know the notations used, so that's one problem. So you start with a psi, which is a single determinant. I'm using the notations I think that is used by Szabo and Oslund. So a trial psi, which is a trial n spin orbitals. Is that the notation used? Hello? Yeah.
Actually, the right one is not. It was like
Yes,
arrow,
yes.
What is arrow?
angular bracket, angular, uh,
Okay,
like
it doesn't matter. So you're saying like
okay.
this, like this.
Sir, he's saying the
Yes,
case.
yes.
Yeah. So these are my spin orbitals. Try to understand. The symbols are not important. So I am making a wave function based on n spin orbitals for n electron. So that is a single determinant. How many determinants you can make? Only one, right? So if I take one determinant, it means n electrons in n spin orbitals, right? Otherwise, it will become zero because two columns or two rows will become identical. What is the question? Somebody is asking something. Hello, hello. Is it okay? Can I proceed? Ah.
Hello, sir. Can you repeat?
No, I am saying that the Hartree-Fock wave function, the trial wave function, what was the impetus of doing Hartree-Fock? Though the Schrodinger equation is not exactly solvable by a single determinant because it's an interacting problem, we still want to write an best approximate single determinant. To do that, we take recourse to variation method. So how do you write the best possible single determinant? So we first write the determinant as a determinant of n spin orbitals and then apply variation method to obtain the spin orbitals. So then by the variation method, we will know that the energy is the closest to the ground state energy. So I can say that this single determinant is good, is the best. Do you understand the reason we are using variation method? Because variation method says, if I start with the psi tilde and calculate the average value in this manner, and then apply minimization to this average value, then we know that this is always greater than equal to E naught. So the minimum is the best approximation. But is the best approximation within this class. So I am only varying these spin orbitals. Okay, so the variation is done only with respect to spin orbital. Chi1 tilde, chi2 tilde to chi n tilde. So I can say that within the class of single determinant, this is the best. So the class is generated by changing these n spin orbitals. So within the class of single determinant, the Hartree-Fock is the best. Once I have arrived at it, Hartree-Fock provides the minimum energy. And the minimum energy, by definition, is the best because of this condition. Everything is above E naught, so minimum is the closest to E naught. That is our impetus, to come as close to E naught as possible. Is this clear, or do you have any doubt about this? This is the Hartree-Fock condition. Rest is mathematics.
Yes, sir. Understood.
Okay? So we are trying to find those n spin orbitals which will minimize this energy. After that, we go through a procedure. So first is that we make a constraint that these spin orbitals are orthonormal. So that's the first thing. Without any loss of generality, we can say that this is an orthonormal set. So that's a condition. So although we will make the variation with respect to spin orbitals, while varying, we will ensure that the orthonormality among the spin orbitals is maintained. So that's the first condition. If I do that, then one can say that the psi tilde is 1. So that's a technical thing. So if I have n spin orbitals which are orthonormal, then this entire determinant is normalized to unity. So that is the advantage, so I can knock this off. So then my condition becomes, I minimize simply the numerator subject to the condition that the chi A, chi B is equal to delta A. So you vary these with respect to the spin orbitals. So chi1, chi2 to chi2 to chi tilde, subject to this condition. So I am writing this tilde just to say that they are trial function. At the end, the results are the Hartree-Fock results. So is that clear, this part again? So that is my Hartree-Fock condition. So the physics has to be very clear that I am trying to build a wave function which is still single determinant, but then there are so many possibilities of single determinant, right? By changing these spin orbitals, I can arrive at many, many single determinants. So I'm trying to arrive at the single determinant, which is the minimum. So that is exactly what you are doing. So I am trying to knock off the denominator by assuming this. So this brings me to what is called the Lagrange variation. So the Lagrange variation says, if you have such conditions, then what you vary is not the energy, what you vary is the Lagrange, which is the objective function is this, and then you have to have a conditions written in terms of condition being 0, sorry. So that is what you vary. So the condition is chi A tilde, chi B tilde minus delta AB equal to 0. So that's my condition. Delta AB is a number, either it is 0 or 1. Okay. So that multiplied by an undetermined multiplier, sum over it, you can do subtraction or addition, it doesn't matter. That becomes your Lagrangian, and you vary the Lagrangian So make it stationary or vary the Lagrangian with respect to the spin orbitals, of course, but also the new epsilon AB. You can clearly see if I vary with respect to epsilon AB, this does not have any epsilon AB, so it's a partial variation. So automatically this is going to be 0. So variation is basically first order change equal to 0. So this will become 0. So I automatically get back this condition. That's the whole idea. So it does not disturb. So the condition is automatically satisfied in the process of variation. And then I also set up a second set of equations, which are with respect to chi1 tilde, chi-n tilde. Variation. So these two variations, two sets of variation will give me the desired result under the condition. Is that clear? I'm only telling the procedures, not the mathematics. Okay, so let me ask the procedure is clear or not. Then what is done is actually to use a Slater-Condon rule to expand this in terms of the spin orbitals. So we come up with an expansion, and I hope all of you remember this expansion in terms of the chi's. So the expansion is the following: sum over A, chi A tilde H chi A tilde, A equal to 1 to n, plus half sum over A, it's a double summation, chi A tilde, it's a 2 electron integral, which is anti-symmetrized. Is that the notation used? So there is an operator.
Yes,
There is an
similar.
operator here with a half factor. This operator that I have written here is nothing but it's an operator 1 by R12, 1 minus P12. Okay? So that's a very simple way. It's an abstract operator. P12 essentially commutes the 2 which is right of it. So it will be, so you have the Coulomb and the exchange. Both are there. The factor half is important, don't forget. You can write the expression in many, many ways. If you want to knock out the factor half, simply write A less than B or A greater than B. Note that A equal to B, this expression is 0 because of the P12. It's identical, right? Chi A, chi A. So A equal to B not allowed, A less than B or A greater than B. You can take any one of these series and knock out the factor half. They're identical because of the symmetry. I hope that was clear. So if I expand this is already chi A, so everything is in terms of chi A tilde, chi B tilde. Then I can do the variation, first order variation, and the result is what is known as the Hartree-Fock equation. I hope all of you remember the Hartree-Fock equation. It is some operator, Fock operator, finally chi I or chi A equal to sum over B epsilon BA chi B. So this is the result. This is the end result, so I can remove the tildes. So that is my choice. So these epsilons are basically the same epsilons which come up here. And then I can say, again, please note that whether I write epsilon AB and epsilon BA really depends on the notation. It is not important. It's a matrix thing. And this is what we call the non-canonical equation. I mean, again, just going through just the procedure without doing the mathematics. So first I come to the non-canonical equation. Then I say that this F operator, and these are steps, is a Hermitian operator. I hope all of you... yeah, I will write the F now. Just 1 minute. Let me write it out. So F is a one particle operator. Let's say F of 1. That is H of 1 plus sum over B integral chi B star 2 1 by R12 1 minus P12 chi B2 d tau 2. So this is actually a one particle integral because here also everything is summed up. Coordinate 2 is summed up, but you use one of the spin orbitals. Now I can use tilde, I need not use tilde, it doesn't matter. At the end, tildes go out. So when I've converged, tildes are not necessary to write. So this becomes my Fock operator. This is very interesting operator because this has a actual one particle operator plus a Coulomb averaging over the chi b. Chi b star 2 chi b is, so all one electron and the rest of the electrons in B, I am summing over B, not summing over electrons, because that's one and the same thing. This is a dummy index anyway. And then I take all the effects of the average effects of rest of the electrons on the electron 1. So that is what is being done here. At least the first part is very easy to understand. The second part is basically the first part with an exchange effect. So that is the interpretation of the Fock operator, that it's an average process of the all interaction on the electron 1. Yes, now ask the question. Yeah. Yeah, somebody is asking something?
Hello, sir.
Yeah.
Hello.
Yes,
Sir,
please,
why it
please.
is called non-canonical?
Oh, that is just a name.
Sir,
Canonical equation is when I have an eigenvalue equation. Because it is not an eigenvalue equation.
oh, yeah.
So that's all. I mean, this is, don't worry about that. It's only a mathematical name. I mean, sometimes you people all get more hooked up with some definitions and so on. Try to understand the physics. The physics that I'm saying is that this is the equation which is not an eigenvalue equation of the Fock operator. That is all that I'm trying to say at this point. However, this operator is a Hermitian operator. Okay, in that case, I can always find a unitary transformation. And I transform the spin orbitals such that the F operator eigenvalue equation can be reached. So as you all know, as it's true in matrix, it's also true in operator. And then the interesting thing is that any unitary transformation of this operator will, so basically if I transform the spin orbitals, what I mean by unitary transformation is transforming the spin orbitals. So if I transform the spin orbital set chi a to some chi a prime by unitary, but this is a vector of functions, I can just transform this into another set of functions, then the Fock operator remains invariant. And that's a very, very important thing. So it all now requires to find a suitable transformation such that this operator can be brought to an eigenvalue equation. Okay, or diagonal form, you can say. With that transformation, I can now write the equation as F chi a, and now basically it means that this epsilon matrix becomes diagonal. So this becomes epsilon a chi a. So one way to formally prove this is the following, that first you define that the F is Hermitian. So how do you show it? You show that the F is Hermitian. Operator. This is an operator. Because of this, so this is statement 1. The statement 2 is that the epsilon is a Hermitian matrix. Now actually the matrix jargon comes in. It's very easy to show that if F is Hermitian operator, this is a Hermitian matrix in an orthonormal basis. Remember, these bases are orthonormal, right? As soon as I bring it, now I say make a unitary transformation U dagger epsilon U, which gives you a diagonal matrix. Let's say I call it lambda or whatever, and I can call it epsilon, doesn't matter. Later I can change it. So this was a non-diagonal matrix. I make a transformation. So in that base, that transformation, F remains invariant. The operator remains invariant. Then using epsilon A as the eigenvalues, so instead of lambda, I wrote lambda just there to show that they're different, but I can now replace it. I reach a canonical equation, which is F chi a equal to epsilon chi a. Right? So this now becomes the canonical Hartree-Fock equation because it's an eigenvalue equation, and this is easy to understand. So this was a very, very important procedure from starting from here, the non-canonical equation to the canonical equation. Through the process that I understand F is a Hermitian operator. First of all, derivation of this. This is the Hartree-Fock. So derivation comes from here. Variation of Lagrangian, right? So you got a non-canonical equation. Then you notice that this is a Hermitian operator. If it is a Hermitian operator, this is a Hermitian matrix. If it is a Hermitian matrix, I can always find a unitary transformation. So that's the transformation I found. This diagonal lambda, I'm now calling it epsilon. It doesn't matter. The unitary transformation makes this invariant. And then I get whatever is eigenvalues. In terms of that, I can write this. Is it clear, the procedure? The basis set will come now. Hello? Hello?
Yes, sir.
Is it clear?
Hi, yes.
Okay. So this is a very, very important step. So first is there's a mathematics here to write this in this form. Then there is a calculus of variation to bring you here with F defined like this. Then the steps of making to canonical. Then what we do is apply this to restricted Hartree-Fock. And that is what has been done, which is a closed shell system where each special orbital is W occupied. That brings you spin orbital. So we are using phi 1 to phi n by 2 special orbitals, each of them W occupied. So I can generate n spin orbitals, and then I go back to this canonical equation and do a spin integration. So the next part has been, I'm sure this has all been done, spin integration, and then you obtain a Hartree-Fock, which I call RHF equation, in terms of only orbitals. So you have very similar equation where I can write now F phi I equal to epsilon I phi I. Very similar to this equation, except that these are now special orbitals. These are the same orbital energies, which was written as epsilon A. I can write now epsilon I. These are all dummy indices, so it does not matter. The only point is that the F has a slightly different form, which is H of 1, but summation is now over n by 2 spatial orbitals. So instead of here, which was n spin orbitals, this was n b equal to 1 to n. Now this is over spatial orbitals. Otherwise, it is identical. And then I write in the same manner phi b star 2, 1 by r12. But the difference is that the Coulomb term is multiplied by factor 2. The exchange remains as it is. So phi b star 2, 1 by r12, 2 minus p12, phi b2 d tau. And this, of course, must have been explained that if I take this one electron with alpha spin, then the Coulomb part comes from either alpha or beta, because you have the same spin here, the chi b star 2, chi b2. So if you see, both of them have coordinate 2. So each of them can be alpha or beta. So the Coulomb contributes twice. But when I do the exchange, because there is an exchange here, this spin must match the spin of the original electron. So if this was starting alpha spin, this also must be alpha spin. So only once the exchange term occurs, right? I hope that has been explained. So that is why this is a very, very important part, that when I do spin integration, the Coulomb occurs for all pairs of electrons. Exchange occurs only with the alpha spin. For the Fock operator and also for the energy. The same thing happens to the energy. So with this little change and everything in terms of spatial orbitals, I can use the RHF equation. And then I can write down the energy exactly in terms of the spatial orbital. So A equal to 1 to n by 2, HA plus sum over AB 2 times JAB minus KAB. I hope these are all done, right? Whereas JAB is the Coulomb integral of phi A, phi B, 1 by R1 to phi A, phi B. I hope you understand what I mean. It's a Dirac notation, phi A star 1, phi B star 2, phi A1, phi B2. 2 electron integral KAB is nothing but phi A, phi B, 1 by R1 to phi B, phi A. Now, there is nice translation. These are over all A and B of n by 2. But you can,
Hello, sir.
yes.
In the Fock operator, there is H1 or
Yeah.
particle, but in the energy expression, there is two factors comes out.
Yeah, because this is the Fock operator, but when I'm doing energy, I have to sum over all n spin orbitals. So the energy expression has n spin orbitals, right? Yeah, n spin orbitals.
Yes, sir.
So I have alpha and beta.
Ah.
So it becomes 2 times HA. So the Fock operator expression, and this is completely different. This comes from here.
Oh,
After I
so
append, I simply do spin integration of this term. So that is why this is 4 times. This Coulomb term is 4 times. This can be alpha or beta independently. This can be alpha or beta independently. With the half, it becomes 2. I hope all of you have done this well. When you have exchange, then AB has to be all alpha or only all beta. Here it's a complete integration. Do not confuse with the Fock operator. Fock operator is a function of 1 electron. So this integral also is an incomplete integration, only over coordinate 2. Right? Because it has to be sum of 1. Whereas energy is a scalar number. So all variables have to be integrated. So this is 1 electron, this is complete 2 electron.
okay.
It is the same spirit, but don't get confused. So this is coming from half into 4 minus half into 2. So that is how this factor 2 is coming. I hope spin integration, all of you should be very comfortable. So that is how this comes. And this is a very, very important result. So for example, if I apply this result to hydrogen molecule, where there is only 2 electrons, and both of them are in sigma G, right? So what will be the energy? Just look at this expression. 2 times sigma G is my A, sigma G, H, sigma G, right? So as if its own one coordinate is having 2 times. Correct? Please tell me if there is any problem. N by 2 is 1. So there is only 1 term. Then plus, this is only 1 term. A is also 1, B is also 1. So this is only 1 term is there. 2J sigma G minus K sigma G. Right? Is this okay? I've just literally translated this. There's only 1 term. But then you see the J sigma G and K sigma G is identical. Because if A and B are equal, then JAA is equal to KA. Is it clear? Because interchange doesn't do anything extra. A is equal to B. Which means 1 cancels this and you get a result which is 2 sigma GH sigma G minus J plus J sigma G. That's it. I hope all of you can apply this, and this is a very intuitive thing finally. What does this say? It says there are 2 electrons, each of them has this H, so 2 times this, wherever sigma G is there. And this is only a paired electrons, so there is going to be a Coulomb interaction of that orbital. There is no exchange. Although here it appeared there is an exchange. So that is a little confusing part. I'm again repeating. From the explanation, it looks like there is an exchange even if A is equal to B. But the point is, if A is equal to B, the Coulomb part which comes twice actually cancels this, leaving you only the Coulomb part and not the exchange when A is equal to B. If A is not equal to B, then of course the exchange part can be there. So for example, if I now have another system where this and this, but now the spin becomes important, 1 and 2. then we can show that the energy is H11, which is basically HA, which is 1H1 plus H22, because now the two electrons are in separate orbitals. But now there is a Coulomb interaction between J1 and 2, and there is also an exchange interaction, minus K1. Now, this is a little bit difficult thing to derive, because your derivation that has been given is on the basis of only RHF. Okay? This will actually require a UHF derivation, unrestricted Hartree-Fock. So we are not done that. But I'm saying in general, there is a theorem from here that every pair of electrons, whether parallel or antiparallel, every pair of electrons contributes a J or Coulomb. However, every parallel pair of electrons contributes to K, only parallel pair. So, for example, there is a parallel pair here, so that's why minus K1 to come. And of course, whenever there is a K, K always comes to the negative sign. So, minus K1. Whereas here, there is no parallel pair. It's only anti-parallel pair. So, there is only J. Now, we are not deriving this general thing because we have done only for RHF. So, RHF is very easy to see. So, I do take another RHF, like a beryllium atom or 4-electron system with the orbital, special orbitals 1 and 2. So, what will be the result? Can you write 2H11 plus 2H22 plus how many pairs are there? One pair is between 1, so J11 plus J1, J22. How many pairs of electrons are there between 1 and 2? 4. This with this, this with this, this with this, this with this, right? So 4J12. That's it. All pairs are counted. How many exchange will be there? Up, up, down, down, minus 2K1. That's it. I can straight away write. This is an application of my formula here for the restricted Hartree-Fock. That is very easy, but I am saying that if you know the recipe that I have written, even for any determinant, you can write it in terms of J and K, a spin integrated formula. These are all spin integrated because everything I'm writing in terms of special orbitals now. I hope all of you can do this. Has this been done?
Yes, sir.
Yes. So you can understand there are 4 electrons. So how many pairs will be there? 6 pairs. Each pair will have a Coulomb. So you can see this 1 plus 1 plus 4. That's 6. That number you must count. Otherwise something is missing. But there are only 2 parallel pairs. So there is only 2 here. So this is a very, very important thing that will come back, that the Coulomb interaction is there between every pair, whereas the exchange interaction always comes with a parallel pair. So for example, if I have 2 degenerate systems, 1 and 2, I hope this is also done, 1 and 2 orbitals, and I have 2 configurations, this, another configuration, this. Now it is degenerate, so basically I mean H11 is same as H22. Then if I write down for the system A and system B the energy, so what would be the system A energy? It will be H11 plus H22, okay, plus, now how many pairs are there? Only 1 pair, so plus J12. But there is a parallel pair, so there is a minus K12 here for the system A. For the system B, it is identical, H11 plus H22, but I have only an anti-parallel pair, so it is going to be J12, and I stop here. Is it clear? I've taken a very simple 2 systems of a degenerate orbitals, so I have just written it down. By my formulae, this has nothing to do with restricted Hartree-Fock. Now I'm using my general lessons. I have derived it for restricted Hartree fog. I'm generalizing it. So none of this is restricted Hartree fog actually. But I can write this as H11 plus H22 plus J12 minus K12. Here I stop with J12. Is it clear? So while you have done restricted Hartree fog, please understand the general statement for any determinant. This is true for a determinant, okay? So you can see now that the integral K12, which is missing here, which is an exchange integral, basically, which is available in system A, parallel spin. But all these integrals are actually positive. Now, this is something that I will not prove. So even K12, which is phi 1 star 1, phi 2 star 2, 1 by R12, phi 2 1, phi 1 2, right? Deta 1, deta 2 is a completely positive integral. Since they are positive, you can see that the energy of A will actually be lower than the energy of B. Is this clear? And this is basically the Hund's rule. You all read in chemistry Hund's rule. Now you see, I'm trying to derive the Hund's rule within, of course, the Hartree-Fock picture. Please understand, that is also a limitation because all that I'm doing is in a single determinant picture. And later on, I will say that single determinant picture is not good. But roughly, the Hartree-Fock is the dominant part, so this is roughly true. So Hund's rule, in a way, is an approximation, but the rule is quite good. So it says that if you have two degenerate orbitals, they will do parallel spin. And they will not even become anti-parallel. So for example, I can take a system C, if you are worried about that. System C, I can write down the energy. Energy is 2H11 plus, again, just J11. But now, this was 2 here. J12 is identical to J11, is identical to J22 because they are degenerate orbitals. By symmetry, you can actually prove. So this is nothing but J12. And H11 is also same as H22. So this energy of C is actually nothing but the energy of B, where K12 was missing. So within the degenerate space, as long as they're antiparallel, you will always get same results. So the only result that will be different is when they have a parallel spins. And that leads me to the Hund's rule. The degeneracy here was crucial because otherwise I could not have compared. 2H11 was equal to H11 plus H22, right? That would not have come. J11 is equal to J12. That would not have come. So in a degenerate space, so this was a very, very important part to understand, okay? And that's a great understanding that we have. The effect of spin on exchange. So only parallel spins have exchange, anti-parallel spins do not have exchange within the single determinant. Within, again, the single determinant. Please remember this. All right. Having reached the canonical equation in space orbitals, okay? So let me first explain that this phi A, each of the phi A is written in terms of atomic orbitals, and this is done after I reach this Hartree-Fock equation. So let's say I write this as sum over mu, C mu A, and the atomic orbitals A mu. Okay? And then I apply this to the Hartree-Fock equation here. And do a projection by these members of the atomic orbital, complex conjugate, you get what is called the Hartree-Fock-Ruth-Hahn equation in a matrix form Because now what I'm writing is that these phi a's are linear combination of the known basis functions. So the combination coefficients are the unknown, and I get a matrix equation which is written as Fc equal to Sc. I hope this is done. And this is exactly the same thing that you would have obtained by variation method. Remember, the S is because this set is a non-orthonormal set. Non-orthonormal set because they consist of atomic orbitals of different atoms. So this is my Hartree-Fock-Ruthan equation, which is what I solve, given these atomic orbitals. And I can obtain the energy, the coefficients. But this is now in all over AO basis. So this F matrix is in this basis of atomic orbitals. C is this coefficient, which is atomic. So C is the only one which connects molecular orbital with atomic orbital. And note, however, that although I have n number of spin orbitals, I would have to take as large a basis as possible, because this is a mathematical expansion, LCAO. So here I should not limit myself to capital N. So K should be much larger than N. K should be much larger than N. In principle, infinity. Of course, infinity is not possible. That is where, since K is a finite number, the errors that come would be called the basis set error. So that is where the basis set will become very, very important. What are the number of basis functions that I do? I hope all of you have derived this Hartree-Fock-Ruthan equation, right? I'm not doing it. In the variation problem that I had given, it is very similar problem. This is exactly how we get. Then these atomic orbitals, which are known, which are supposed to be known basis, they are usually Slater function. Because all of you know what is Slater function. It is exponential minus some zeta times r. Or more rightly, r minus Ra, where Ra is the coordinate of the atom A. Okay, so this is something like this, plus some constant. This is proportional to this. You can have r square, r cube, but basically S functions just have this. But if you take these A mu's here as a Slater function, what turns out that the calculation of all these integrals in F becomes much more complicated. They have what are called 4-center 2-electron integrals. I am not writing the F matrix because F is a matrix over atomic orbitals. So you can write it in terms of the 2-electron integrals. And this becomes very, very difficult to solve in Slater orbitals. So what is done is a further studies which are done before you actually do the Hartree-Fock, is that we know the AMUs in terms of the Gaussian orbitals. So many times these are called primitive Gaussian, and then the Slater function becomes contracted Gaussian. As if I have contracted some Gaussian to bring these CGTO or contracted Gaussian. Number of Gaussian functions that are required to contract also comes in my definition of the basis set. So two together is the basis set. One is the number of atomic orbitals, which can be called CGTO, which are mu, and number of Gaussians. These are basically Slater, but I can't apply Slater, so I'm approximating a Slater by a combination of Gaussian. Number of Gaussian functions for each Slater. And in each case, there is an error, because this should be infinity, this should also be infinity, because each of the cases I'm writing an 1-electron function as a linear combination of another 1-electron function. The same thing here, right? So this is also 1-electron function, and Gaussian has a characteristic that this becomes quadratic, square. And if you have a square, it can be shown mathematically that these 4-center integrals can be reduced to 2 centers or 3 centers. So the calculation becomes much simpler in Gaussian. So that is why Gaussian is preferred, but it adds to a further level of approximations, further level of complexities, but it is still better eventually. So these are the two major errors for the basis set. How many number of atomic orbitals, and how have we expanded the atomic orbitals in terms of Gaussian? So your results of Hartree-Fock depends on the basis set. So there is nothing called no unique Hartree-Fock, unfortunately, because I am not able to solve these exactly. Up to here, it was exact. Remember, up to here, it was exact. Approximation to Hartree-Fock start here. That I use k number of atomic orbitals, then I use a Gaussian expansion for each atomic orbitals. So these are two levels of approximation, and that means there is no unique Hartree-Fock. If I make this infinity, then this will become exact. Is it clear? So I have different types of basis sets. So let me just explain one with the 631G. It means dash separates core and valence. It means first I will look at the number of atomic orbitals. For carbon series, carbon, etc., oxygen, nitrogen, etc., first row. So this means I have only one number before the separator. So the core is only one. So there is only one as function, only one function. Then there are two sets of functions after the separation. So this is the valence. This is a core and this is a valence. And valence is for carbon 2s and 2p. So there are two sets of 2s, 2p. So let me call it 2s, 2p and 2s prime, 2p prime. Please remember, these sets come because the number of entries is 2, nothing to do with 3 or 1. So total number of atomic orbitals for carbon is this. This is called double zeta valence. So valence has been double zeta. So what is the total number? 1 plus 1 plus 1 plus 3 plus 3, right? So total number for carbon here is 9. And you have to add up. If you do hydrogen, oxygen, you have to add up. Where is 631 is coming? 6 is coming here. For the 1s orbital, for the second level, number of primitive Gaussians is 6. For the first set of valence orbital, the same number is 3. And the second set, it is actually only 1, uncontracted. So how do I expand this Slater to Gaussian? Is these numbers. But the number of atomic orbital does not depend on 631. It just depends on number of entries, right and left. And that is important for Hartree-Fock, because in the Hartree-Fock, actually I am using only this number in the Rutherford equation. So the matrix of Rutherford equation, the K, is determined by this number. So if I do 61G for hydrogen, then hydrogen has a valence, no core, so both of them are here. So it is 1s, 1s prime. So if I do a calculation for methane, then what is the total number of Slater orbital? It will be 9 here and 2 for each hydrogen. So it will be total number will be 17. So my entire Rutherford equation is 17 by 17 matrix, Fock matrix. Each of them will be, of course, expanded by 631. That's a different matter, primitive Gaussian. So I will have 17 atomic orbital energies. But methane has how many electrons? 10. So Hartree-Fock will use only 5 of them. The rest of them will become virtual orbitals or unoccupied orbitals. You might have already heard this. And that will be very, very important when you go forward. All right. So I will close it here. I don't know if Professor Sangita Sen has come. But let me stop. So can you ask the question, what was the problem with the basis set now? Of course, the basis sets have several other things, polarizations, diffuse functions, and so on. I'm not speaking of that. But let me ask any question about basis set, that what you have.
No, actually, I had the problems that there are many kind of basis sets.
Yes.
I had some problem with those nomenclatures. Like here,
Oh,
this is the case of 631G in
right,
that
right.
way.
So what is the problem? Let's say I do a triple zeta valence. So if I just give you 6311G, this is triple zeta valence because this is same number of entries here 1, here number of entries 3. So that means the valence has been tripled, right? If you now with any of these 631 or 6311G, you put star, then you have put a polarization function on the carbon, oxygen, etc. And so that is D function. And for hydrogen, it is P function. If I put double star, if I put single star, the hydrogen doesn't have polarization. Okay? And then you can add diffuse functions. Okay? So many times it becomes very cumbersome. Diffuse functions are given as plus plus. So many times they write in the following manner: 631G bracket D comma P, which is polarization, and then plus plus. Plus plus is diffuse function for both hydrogen and both carbon. Hydrogen like in carbon. So the nomenclatures you can keep varying. That's not important. The important thing is that this is the. I can also have two polarization functions. So sometimes I can have 2D, 1P. So that's why people prefer to write in a bracket. After the valence, how many you are adding? You can have quadruple zeta. So 4 entries in the valence. Number of polarization function, write it here. Then diffuse function, write plus plus. Diffuse function is usually one set of valence orbital. What is a diffuse function? They are basically a valence orbital, one set of valence orbital. So that's why plus plus is enough, one set of valence orbital. So basically S and P with very small exponent. So exponent is very, very small. So if it's Gaussian, this is a large tail. So if you have a long range interaction, they can be easily trapped. So anion, for example, weak intermolecular interaction, which is a very long range effect, which does not go away. So many of those you require diffuse functions, sometimes excited states. So diffuse function, without diffuse function, the calculation becomes meaningless. Yeah, just 1 minute. Hello. হ্যাঁ
আপনি জয়েন করবেন তো?
হ্যাঁ 10:15 and join.
হ্যাঁ হ্যাঁ, আর you will introduce her.
Yeah. Okay, and after that you will conduct.
উনি যে বায়োগ্রাফিটা পাঠিয়েছেন ওটা আমি আপনাকে WhatsApp এ পাঠালাম।
আমার কাছে আছে।
She has sent.
Oh, she has sent.
She has sent a short bio.
Okay, fine.
So that I sent to you.
Okay, thank you.
Okay.
All right. So I think there are many variations you can keep doing. So diffuse basis functions are not just unique. You can keep changing your basis functions. Is that okay? Nomenclatures, people have different nomenclature. This is the nomenclature that is used in Gaussian, but olden days Dunning and Husinaga used to use a different nomenclature. But this is the Popul's nomenclature, which is probably more standard, so I'm just writing that. So basis set is more of an, nomenclatures and all that are more of an art. You just have to, but the science is only this expansion. And of course, you have to have experience in a basis set. What works better? But I can tell you, more the merrier. So more number you add, always better. Okay. Any other question? I am more or less, the 1 hour was actually taken on the review. But I want to start next class on the beyond Hartree-Fock, the post-Hartree-Fock theories, which actually is generally what is called electron correlation, theories of electron correlation. Okay. I hope the word electron correlation has been introduced. So let me now stop sharing the screen, and let's see if, I think the Professor Sen has joined. So Sangita, I actually, by request, I did a review of the lecture, the Hartree-Fock, more or less just the steps. I did not go very great detail in mathematics, but I think if you see the screen, I will share it once again so that it makes it easy for you. Can you see the screen?
Yes, I can.
So you can very quickly see what all I did. So I just said what is Hartree-Fock, apply the variation method, use the variation method, then minimum is the best basically it's the variation with respect to this. Minimum is the best within the class of single determinant. The Hartree Fock provides the minimum energy, and that is best because of this variation method. So I also explained that this is a choice. So within this choice, it becomes a constant variation. Minima is only this subject to this. So that brings it to the Lagrange variation, and the Lagrange. Then I expanded this, and that brings in to the Hartree-Fock equation, which is non-canonical because of this. And then I said F is Hermitian operator, hence epsilon is a Hermitian matrix. You can do unitary transformation to bring it to a canonical form. So this is what I just wrote down, that F remains invariant, etc., etc. And after the canonical equation, then I particularly wrote about the RHF, the same thing in the basis set with the factor 2 here, and wrote down the energy expression, and then generally expanded the idea of every pair giving a J and every parallel pair giving a K, although that cannot be explained only by restricted Hartree-Fock, but the idea is extended to any kind of determinant. And that tells you also the Hund's rule. So I explained the Hund's rule with two types of determinant here, that A is lower than B because of K, and the same goes for a degenerate pair with C because of these equalities. So C and B are equal, A is the lowest. So that's the Hund's rule. And then I introduced the basis set towards the end. That the basis expansion, and that's the Ruthan equation. And then the idea of Slater not being good and coming to the Gaussian primitive. So it's a very, I should say, just an executive summary. Okay?
Yes, this is a very nice summary.
So then you can now take it from here. And I think you can discuss the deficiencies of the Hartree-Fock, because the next class I'm going to take on the CI. So why is Hartree-Fock bad? And why do you require why do you have?
Okay. I will start with the mid-sem question paper because
Okay,
I had some
that's fine.
requests. And
Okay,
then,
that's fine. So I mean,
and
just
then
use
I'll
this.
go on to the deficiency.
Just use this hour any way you want, no problem.
Yeah, sure.
So I will come back on Thursday. Thursday's class is what, 10 o'clock?
Thursday's class is also 9 o'clock.
Oh, it's also 9 o'clock. Okay, so I will see you on Thursday with the variation method, and I also request all the students to join classes in time, because by the time we are
the
coming,
9 o'clock class is always a problem. I have been telling them, but
yeah, but Thursday's class is also 9 o'clock. That's a problem.
It's also 9 o'clock.
Yeah, so we'll tend to get less and less time. So that's what I'm requesting all of you to come in time. Okay. All right, Sangita, I'll have to leave now.
Okay, sure.
Because of the Women's Day program. Yeah. Okay. Thank you. Yeah. Okay.
So could one of you just stop the recording and restart it once more so that the two classes are separate?